Hello, welcome to the online edition of the SAS Global Forum 2020. My name's Gordon Brown, I'm from SAS. Today I'm going to talk to you about new procedures in SAS Visual Statistics 8.5. If you're not familiar with Visual Statistics, it's a product that sits on SAS VIA. 8.5 was put out in the fall of last year. Specifically today, I'm going to talk about 4 new procedures that were released in SAS Visual Statistics 8.5. The first one is PROC GAMSELECT. This procedure allows you to do model selection for generalized additive models. The second is PROC Sandwich. PROC Sandwich uses a robust variance estimation method to perform analysis. The third one is PROC SIMSYSTEM. SIMSYSTEM generates data based on the moments of a distribution. And the last one is PROC NMF, which stands for non-negative matrix factorization. Here are some of the procedures that are available in Visual Statistics that allow you to do model selection. The first one listed is GenSelect, which allows you to do model selection for generalized linear models. LogSelect is for logit models including multinomial. PHSelect is for Cox's proportional hazards model, which is for survival data. QTR select is for quantile regression. Reg select is for ordinary least squares. And the new one is GAMSELECT, which allows you to do model selection for generalized additive models. So let's talk a little bit about GAMSELECT. As I stated, it is for doing model selection, but it specifically works on splines instead of working on the individual parameters. So what happens in GAMSELECT is you do not have to specify the functional form of the potential predictor variables. GAMSELECT will figure that out for you. So the spline terms are used to determine that nonlinear dependency. So is this going to be quadratic, cubic, etc.? You don't necessarily know. You don't have to worry about it. GAMSELECT will figure that out for you. In addition, it will provide graphs which will allow you to see what these distributions and functions look like. The default method in GAMSELECT is boosting, but there's also the shrinkage method available for model selection if you wish to use it. Here's an example, modeling mortgage applications using the GAMSELECT procedure. And here you can see syntax that should look fairly familiar to you. We have a class statement, which allows us to specify classification variables, and we have the model statement. In the model statement, after the slash, we specify the distribution equals binary. That tells us we're going to be looking at a binary distribution. The event we are most interested in is when the variable bad takes on the value 1. That is going to be our outcome of interest. To the right of the equal sign, we have our independent effects. The ones that have the param statement in front of it mean that they're going to be modeled as is. There's not going to be anything done to those. The ones with the spline statement in front of it, such as spline CLH, are going to use a spline term in order to model the outcome of interest. In addition, we can include interactions such as loan and value and mortgage and value. At the bottom of the procedure, we have the selection and the partition statement. The selection statement allows you to choose the method. In this case, we chose boosting, and the partition statement allows you to create both the testing and training data set for performing validation. Here are some of the output. You get fit statistics. You can also get betas if you want them. But in this case, I'm showing you the graphs. On the right side, in the graphs over there, you'll see 4 separate graphs. The 2 at the top, one is for CLH, and it shows its functional form with respect to our outcome of interest. Same with the det I and C. The bottom 2 are for the interaction. So that's the value and mort due interaction and the value loan interaction. And here you can see how these interactions are affecting the outcome. Where you see the bright red, or the brightest red color, is where the event is most likely to happen, and where you see the darker colors is where it's least likely to happen. The second procedure we're going to discuss is the PROC Sandwich procedure. And PROC Sandwich uses a robust variance estimation method to perform analysis and inference. In this case, we're going to be using the classic robust sandwich estimator. Now, the beauty of the sandwich estimator is that you, the user, do not have to specify the correlation structure within clusters. The sandwich method we'll look at the clusters and we'll change the variance accordingly to take into account misspecification of the correlation structure. As a result, this method is very useful when we have a lot of clusters, as we no longer have to worry about what that variance structure is. The sandwich matrix will figure it out for us. Here's an example of using microarray data with the sandwich procedure. So again, here's some syntax that should look pretty familiar to you. First we have PROC sandwich, and we specify that we want to use the microarray data from the MyCast library. We have the class statement, so we're specifying some variable as categorical variables, and then the model statement. Our outcome of interest is density, and then we have gene, treatment, dye, and a few interactions. Okay. Our cluster statement tells us that microarrays are going to be our cluster. So what's going to happen in this case is we're going to fit a linear model for density based on the independent effects specified. We're going to use the sparse option for sparse matrix techniques. Microarray is going to be our cluster, and so we're going to get the sandwich estimator for the variance based on cluster, which is microarray. So here's some of the output that we can see from PROC sandwich. We ask for the type 3 model and NOVA table, and that's what we get in the lower right hand corner, which shows us which effects are significant, or more importantly, it gives us the F value and the P value. And again, all these tests are based on the sandwich estimator, so we don't have to specifically request the sandwich estimator in this case, it's automatically determined for us. The third procedure is the SIMSYSTEM procedure, and this is a procedure that you can use to simulate data. Now, it's specifically for simulating data from a continuous univariate distribution in either the Pearson or the Johnson system. The whole idea of SIMSYSTEM is instead of trying to specify parameters, you simply specify the moments. So in this case, you can do the mean, the standard deviation, the skewness, and the kurtosis. This allows you a lot of variability in the type of data you want to simulate. So let's look at a simple example. This is a case where I'm going to be simulating data from a distribution that has moments as specified. The mean is 5, standard deviation is 2, the skewness is 1, and the kurtosis is 4.5. So down in the syntax, you see I'm specifying the system as Johnson. The n equals 10,000 means I want 10,000 generated observations. I'm using a seed because this is pseudo-random numbers, and I want to make sure I can replicate my results. My moments are then specified in the moment statement. Mean equals 5, standard deviation equals 2, skewness equals 1, and kurtosis equals 4.5. This is going to generate a data set, and it's going to be stored in the MyCast library as the SB data set. Here's another example of things that you can do in PROC SIMSYSTEM. On the left, I have the moment ratio map for the Pearson distribution. And this tells you what type of Pearson distribution you will get for values of kurtosis and skewness. For example, if I specify a skewness of 0 and a kurtosis of 3, I get the normal distribution, which is illustrated by that blue circle on the graph. You can also see a series of x's moving across that graph. And those x's are represented by the graph on the right side. That's centered and scaled Pearson densities n equals 0. What's going on in there is I'm changing the value of the skewness, I'm making it larger, but I'm keeping the kurtosis at 3. And you can sort of see what happens. The larger that skewness gets, the more peaked that distribution becomes, and you can see the shape of that distribution. The last procedure we're going to talk about is the NMF procedure. And that NMF stands for non-negative matrix factorization. So the whole idea of the NMF procedure is to take some matrix X, and I want to decompose that matrix into two new matrices, or two low-rank non-negative factor matrices, W and H. W is going to be the features matrix, and H is going to be the weights matrix. Once I get these two new matrices, I can use them for a variety of different things, including dimension reduction, feature identification, and feature extraction. Thank you very much for listening to my super demo. My name is Gordon Brown. Here is my contact information if you have any questions.